Greetings and salutations, tech artists. We are continuing our journey into AI, and we just started with the introduction of things. We got a bit of a slow start last week, but we're going to sit going and continue on. And we're going to jump right in and continue where we have left off. And let me pull this up here. Nope, we don't want to see that. What we do want to see is this. All right, these are the steps we're going to follow in creating any kind of AI model that we can generate. We're first going to load and visualize the data. Then we're going to edit the data, which means we're going to reshape it, we're going to normalize it, and we're going to categorize it. And that's important because we are creating learning models. And this is going to be um, learning where we are going to associate with it. It is going to be um, we are going to work with the data itself. We're going to create the model, then compile the model, then train the model with our data. All right, so let's get things going from whence we left off on last week. All right, I'm going to start this thing up by clicking on the start here, and I'm going to look for my Anaconda shell. All right, there's my Anaconda shell. Hopefully you can read. Oh, there it goes. We can make it bigger. All right, now it says up here there's a base because I don't remember what the environment was. So we're going to have to remind myself what is the environment. And so I want to look at my Conda environment list. I click that. And so those are all of my current environments. I'm going to make my window a little bit bigger so I can see what's going on. Okay, we want TA demo. That's the one we were working for. So I'm going to activate this, and I do that by saying conda activate TA20 demo. Hopefully you can see all that. Hit enter. Yep, the little name changed here, and so we know we are in the right place. So let's go ahead and run Jupyter Lab. Whirling, twirling, starting up. All right, here we go. Here's my Jupyter Lab. And let's see if we can make this just a wee bit larger. That's a wee bit bigger. Hopefully you'll be able to see all this. All right, we created a new file in our Jupyter lab called MNIST intro. And just give a quick interpretation of what we did last time. During the first day, what we did was we imported Torch, Torch NN, which is the model environment, the Torch utils, which contains the data set and the data loader, and the optimizer called Atom. We're going to load those in. It's going to take a little bit. And then we're going to load in something called Torch Vision. Torch Vision is what we're going to use to actually transform the images around here. And we're going to use matplotlib in order to visually see the data. All right, then we're going to find out, okay, do we have access to a CUDA, which means do we have access to the GPU to make sure this is run on the GPU, make it parallel processed, make it fast. We're going to test this. And we find out, no, we don't have access to CUDA. We don't have access to the GPU. All we have is access to the CPU. Then we're going to create two data sets. Data sets are a whole bunch of data. And we're going to create a training data set and a test data set. All right, we've got that. So what does a training data look like? We're going to take a look at it right here. All right, it says that it's a number of data points. We need 60,000 data points. Now, those data points are more than just 60,000 variables, 60,000 floats, 60,000 integers. They are 60,000 data sets, meaning that there's a whole bunch of information there, including a 28 by 28 rasterized image, and including there is a label which identifies, all right, what does this image actually represent? All right, and it says here that we're going to use split. We're going to be using this for training. Okay, we're going to take a look at this training data. So we're going to do X0, Y0, and we're to look at training data element 0 or sequence 0. And that's what it looks like. We print it out, and that's what it looks like, and it's kind of hard to tell. And we're going to take a look at what Y0 is. And Y0 says, well, that's a 5. Okay, does this look like a 5? I don't know. We're going to take a look at the type. X0 is an image, and Y0 is an integer. Okay, that's understandable. Then what we're going to do is create a transformer. A transformer is going to transform our just plain old data and transform it into something called a tensor. And where it says transforms, it says to image, and we're going to transform that to the data type of a torch float 32. So turn it into a data type of float 32 tensors. And we're going to scale that to be true. And then we're going to go ahead and enter that. So we've defined what our transformer is. And so we're going to say x0 x0 tensor equals transformer x0 and there. But what does that look like? So I'm going to go ahead and take a look at that right now. And it is a buku of information there, just containing all of the information of what our X0 is, or our image is. And we can see that this is 28 by 28 images, which is basically 720 floating point values. And each one of these floating point values is a value that's going to be between 0 and 1. How do I know? Is because this transformer normalized all of the data, because normally the pixel values are going to be between a value between 0 and 255. But when we're processing this stuff in deep learning, we're going to need to normalize it between 0 and 1. And that's what the transformer does. It normalized that for us. And so we have that. And we're going to take a look at that is. So we're going to employ the matplotlib in order to plot that thing out. And we're just going to take a look and see what this thing actually looks like as a big old tensor. All right. So there is our thing. We see that it's about 28 pixels by 28 pixels, and it's in grayscale. And so let's go ahead and finish up our model here. Oh, there we go. Okay, excellent. All right. On this next cell under here, we're going to define what the batch size is. Okay, a batch size is, we're going to be doing this in chunks of a certain batch number. PyTorch likes to identify things in batches, so we're just going to go and identify things as batch number of 32. Batch size equals 32. So if you, for example, had 32 threads on your GPU, you could process 32 threads all at the same time all together. Now, we're just going to go batch size. It's going to do things sequentially because we only have the CPU anyway, but it doesn't really matter. But what we're trying to do is we're going to create a data loader. A data loader is kind of like a data set, but a data set is not iterable. Oh, I mean, a data set is iterable, but it doesn't really have any kind of index. It's kind of like a big old chunk of data, and it's not very good for accessing specific amounts. So what we're going to do is we're going to create a data loader using the PyTorch dataset. So we're going to say training loader equals, and we're going to look for a data loader, and we're going to look for the training data, and we're going to give it a batch size. So we want to look at the batch size to be equals batch, and we're going to look for shuffle to be true. Shuffle equals true. Okay, shuffle equals means it's going to shuffle up the data value. So when you're training the data, you want to keep it on its toes. You don't want to make it easy on itself. And so what we're going to do is we're going to shuffle it up so that the order is changed every time we execute it. And that's going to say we're going to do the same thing for the test loader. And so I'm going to copy this exact same line again. Test loader equals data loader, and instead of the training data, we're going to use the test data. And then we're going to go with the batch size, the same batch size, and the shuffle to be true. Let's go ahead and execute this. And it seems to have worked sufficiently. Oh, you know what? I somehow ended up with a cell that is not really a cell. It's a kind of like information. There's really not much here. So what I'm going to do is I'm going to copy this and I'm going to enter this again into another shell. I was wondering why I couldn't do the completion, and now I understand why. It's because I wasn't working with a little cell. I should have known that because it didn't have the little square brackets there in front of it, and that told me that it was actually a cell. So now let's do this again and execute this. Okay, so everything should be kosher and copacetic. So now let's build the model. And there's a lot of different ways of building the model, and I'm going to show you one way, and we're going to go into a bunch of other ways and so forth. And you can start building a model by creating a list of layers. And you can identify all of the layers all together, and then you can put them all together and copy them. And so what we can do is here, we're just going to say layers equals empty set. Okay, so we got nothing in here. Now, what we're going to do is we are going to create a little test matrix here. And I want to see if my concept of layers is going to work. So this is just a test. So I'm going to put a little comment here. This is a test. Okay, so I'm going to say test matrix equals torch dot sensor. No. Torch dot, now we just want to torch scalar tensor. No, just tensor. Okay, torch dot tensor equals, so what we're going to do is going to create a little test tensor right now for us, and we're going to create a two-dimensional matrix. You know, the kinds that used to give you headaches when you had to do this for homework in spring semester. Okay, we're going to go 1, 2, 3 in the first, and then we're going to create another little list here. 4, 5, 6 in the second list, and the third list is going to look for 7, 8, and 9. And we're going to finish this off list here by one more square bracket, and we need one more here. All right, and so now we've got, if we want to just test this, I'm going to see what our test matrix looks like. Now we're just going to look for test underscore matrix. I want to see what it looks like just to make sure everything is working correctly. Okay, and so there's our tensor. Okay, easy squeezy. Okay, so the first thing we're going to do is we're going to flatten this out. You see that it's actually 2 dimensions. And what we're going to do is we're going to flatten our test matrix out to be 1 dimension. So we're going to say nn dot flatten, and we're going to go with test matrix. There we go. And we're going to execute that. Okay, and so you see it didn't do anything, but it really kind of flattened things out and got things ready. So we're going to say batch underscore test matrix equals test matrix none through 1. So we're going to we're going to get all the values none through all the way in. And then we're going to take a look at what the result of that is. So batch test matrix. Okay, so it's getting everything, and we've got all the values. And we're going to go take a look at that. So nn dot flatten, and we're going to look at the batch test matrix again, and we should get comparable results. You'll see that right now after we reorganize the data, that it took and still made it a two-dimensional list, but the actual contents in this first list have been flattened out. And we want that to be flattened um, because the data going in has to come in parallel, and our model can only accept data coming into it that is flat. It can't be multi-dimension, or at least the one we're creating is. We're going to create other ones that are a little bit more dynamic later. So let's see what happens if we reorganize this again. So nn dot flatten, and then we're going to do this again for the test matrix. And then we want to get just the whole data, and then say none, square brackets, and in here. And what does this create? Okay, and so that kind of like reorganizes things back to the way it is. So we want to do our end flatten already. So we're going to say layers equals nn dot flatten. And then we're going to take a look at the layers once we created this. Okay, and so there is our first thing. We're going to flatten the contents of whatever we get, and then we are going to is going to be the first operation in whatever model we create. Okay, with that in mind, so let's go ahead and create our MNIST model. And so the input size is, we need it to be, well, 28, one color, well, 28 rows, 28 columns, and each of those columns has one value, which is to be the color. So we say input size equals 1 times 28 times 28. And once again, that means is one color times 28 columns times 28 rows. Then we're going to take a look, we're going to create our layers equals to, and we're going to create a big list here. And we're going to go nn.flatten to be the first layer. Okay, what this is going to do is flatten it out into, say, a two-dimensional array of 28 units by 28 units. It's going to be just one big old 728 units wide. Okay, that's going to be big. All right, and so we are going to designate that as the starting point. And so we're going to create the first layer. It's a linear input here. We're going to identify that as nn dot linear, and we'll get into what linear means in a little bit, but we're going to put this as an input size, and we need to tell it that the input size is that big old number, and we want to go 512. Okay, 512 is a number that works pretty well for this situation, and this means is that we're going to send it to 512 hidden units. We'll get into what the hidden units are. Just go for now that 512 is kind of like a good number to work with. All right, then we're going to use something called a uh, uh, a rectilinear linear unit. Okay, we'll go into what that is next, but I'm just going to declare it, and we're going to go RE Lu, and it's going to be capitalized. All right, so there it is. We'll go into what rectilinear units are in just a little bit here, and we're going to create another layer. So we're going to create this NN linear, and we're going to make it 512 by 512. And we're going to need one more rectilinear layer. Okay, and then RELU. All right, and we're going to finish this off, close this off with square brackets, and let's take a look at what our model looks like. Now, mind you, we're just looking at the layers here. We haven't actually created the model yet. We're just looking at the input that's going to create the model. So we look at that. Uh-oh, we have, perhaps you forgot a comma on line 3. Okay, I forgot here. Let's get the view. I don't know what the line are. If we could show the line numbers here, Shift L, that'll bring up the line units and say, oh, I forgot a comma here, a comma here. Yeah, because remember, we are creating a list here. So we're going to do enter this, and we have another error. ReLU is not defined, and then ReLU. Okay. Oh, I got that was not a point. It was a greater than sign, so not very helpful. All right, there we go. There is the definition of our object. Now, we haven't made it into an actual model yet, but this is the description for it. So we're going to have an input of 784 inputs, and it's going to go out to 512 rectilinear units. And that's going to go to another layer of 512 rectilinear units, and that's going to go into our output. So let's go ahead now and actually make the model itself. So model equals NN dot sequential. Okay, sequential is the model type, and we're pretty much going to be working with all of sequential models during this module. And so the input for that was we're going to say star layers. Okay, star layers is and this is something that we haven't covered in Python, but what this does is it's going to create, it's kind of like the pointer or the memory address of this. And this is where the sequential is going to take the memory of this and still use each layer and use them as their own. Okay, and so I'm going to go ahead and just print out what the model is here. Okay, and there's our model, and that's what it's actually looking like now. So it's now an official PyTorch module. Okay, we have to make sure that it is ready to go to our device, whatever that device is. We're going to say model dot to device, because if we had information going to a GPU, we wanted to go to make sure that it's prepared for the GPU properly. And we're going to go a little test here. Next, model dot parameters dot device, and then we're going to say we're going to finally compile all of the we're gonna run this, and this is going to display all the parameters going into our model. And we're going to say, okay, the device is going to go into the CPU. All right, that's fine. So let's go ahead and compile our model. Just like a blueprint inside Unreal, we can't actually use it until we actually compile it. We're going to go model equals torch.compile, and we're going to compile the model. Okay, that's all seems to be fine and dandy. Everything seems to be compiled as good. All right, now that we have compiled our model, we have to kind of prepare some other information. Well, the first bit of information we're going to create is called a loss function. We'll go into a little bit of what a loss function is, but know that a loss function is essential in order to help train our model. So that means every time we execute our model on some test data, we want it to learn from it, and the loss function tells us how to what's a good strategy for learning? And we're going to call that a cross entropy model, entropy loss, and an optimizer. What is an optimizer? Well, an optimizer is a algorithm that kind of optimizes or makes our reverse optimization all a little bit better. We'll go into that a little bit later. But I just wanted to show that to you, and we're going to use our atom as and we're going to go model dot, and we're going to make it send it our parameters. Okay, we've got that set. Okay, we've got our loss function, we've got our optimizer, and then we're going to collect the size of our data sets. Okay, it's good to know what these things are. So training n equals the length of training loader dot data set. Okay, and then test n equals the length of, what is it, test loader? Is that right? Test loader? Yes, yes, ma'am. Test loader dot data set. All right, and so we're going to print out what these are. So I'm going to go ahead and say training n comma test n. Let's see what these what numbers we're talking about here. Oh, I forgot this needs to be capital N. Okay, so that means our training set is 60,000 units and our test set is 10,000 units. Okay, now every time we train a batch or 32 of our test values, we're going to need to test to see how accurate things are going to. So what we have to do is we have to create a little accuracy function. So we're going to define a new function called def get batch accuracy, and we are going to input some output to it. We're going to put in a label, and we're going to contract how much data or how large our set size is. And so we're going to first predict what our output is. So we're going to go pred equals output dot argmax. Okay, argmax is a function that's going to give us the final values. Now we're going to have altogether, about let's see, about 10 values. And so the output, there's going to be about 10 different values that can come through here. And so argmax kind of figures out how many values we actually do have, and it's going to take that into consideration and output that number of results. So we're going to say dim equals 1 and keep dim equals true. So that's our prediction, and we're going to have our correct amount. So correct equals the prediction dot equals y dot view and as pred, and we're going to sum all those up and then grab them by the item. Okay. And then we're finally going to return the correct amount divided by the total size. Okay, so there is our overall value, and hopefully I typed in everything. Okay, we've gone ahead and then we've created a function. We've created our model. So what we have to do now is we have to create a training function. A training function is a way of actually going through and training all the data. So let's create that training function. So def, we're going to call train. So this is going to train all the specific data. All right, so train, we're going to say loss equals 0. And our accuracy is going to start off also at 0. Then we're going to say model.train. Okay, so what this is going to do is we're going to tell the model that we're going to use you for training. Then we're going to say for x and y in training loader. So we're going to go through every single element in the training loader. There's 60,000 of these. So for every x and y, x is the image, y is the label. So for every X and Y in the training label, we are going to convert each X and Y elements, we're going to send them to the device. So X and Y equals X dot to device, to device, and Y dot to device. All right. Then we're going to actually test the data now because we've got our data from the trading loader. It's loaded, the image is loaded in X and the label is loaded in Y. And then we're going to test it against our model. So we say output equals model X. Okay, so that means we're going to give it the value of the image and it's going to put it into, and it's going to give us an output. Now, remember how we created the output? It's going to end up with 700 and, how big was that? It's going to end up with like 700 and, I believe 742, 28 by 28, whatever that is, I can't remember. So it's going to be that. And now we're going to say optimizer dot zero grad. All right, batch loss. Batch loss equals our loss function. This is the one that we defined earlier. And this is going to be output and then Y. Okay, so we're going to consider what our batch loss is. And so the output is going to be whatever the output was, and Y is going to be our true value. And we're going to try to figure that out. And so we're going to use something called backwards propagation in order to train our model to go backwards and adjust all of the values that we collected all the way. I'll go into this a little bit more further in just a little bit here. We're going to go batch underscore loss dot backward propagation. So backwards, no, batch loss dot backward, and then optimizer dot step. Okay, with that done, let's go ahead and adjust what our loss is because it started off at 0. So we need to do is understand what our current loss amount is. So loss plus equals batch underscore loss. And we're going to look at the item. Okay, for our particular batch loss, what is the current item? And we're going to update this with our accuracy as well. Accuracy plus equals get batch accuracy, and that's our little function, and we're going to send to it the output. We're going to send it the Y value, and then we're going to send it the test size. Oh, actually, we don't want the test size. We want our train size. We want train N. Okay. And then finally, what we wanted to do is print all this out. So we're going to go print, and inside of here, we're going to, okay, let's make this into a current thing. We're going to say F, format. All right, train minus loss, colon, and inside here, we're going to do the loss, and that's going to be at, we want it to do to just 4 decimal places. I'm going to go 4F. And the accuracy is going to be presented off as, and we're going to put inside of here the accuracy, colon dot 4F. And then we're going to finish this off here. Okay, and it says here that I have a, it's giving me an error. Okay, here. Oh, I have to finish off the quote. All right, so here's finishing off the quote and then finish off the parentheses. All right, I'm going to go ahead and enter that. And so there's my train function. I bet I'm typing something in wrong, but oh well, we're going to find out what that is. And then here's our training function. So we're going to have to do the same thing again, but we're going to do is we're going to validate our test data. So we're going to create a validation function. So depth validate, and then we're going to do the same. Say loss equals 0, accuracy equals 0, model dot, instead of train, we're going to say model dot eval, and then with torch no grade, we'll go into what this means in a little bit. So with torch dot no grad, it means no gradient for future it. And then, okay, with torch no grade, so taking into consideration this mode, we're going to say for x and y in test loader, we're going to grab the x and y values, and then we're going to send them off to our device. Then we're going to say output equals model x, just the same. And then we are going to update our loss function. So we're going to say loss plus equals our loss function. And then we're going to get the output. And we're going to send it to the output and y. And then we're going to make it the dot item. And then we're going to modify our accuracy to be basically kind of the same thing here. But instead of going train and, ooh, look at that, I found an error. So that should be underscore n. Let me go ahead and rebake this. And so this should be, instead of train n, this should be test n. All right, so we got that. Now let's go ahead and print out that statement. I'm going to go ahead and copy this print statement. Okay, so print, I'm going to say, instead of train, I'm going to make this valid loss. And so our loss is going to be loss accuracy, and the accuracy is going to be 0.4. Okay, so that should be basically the same. Okay, validated in line 1. Oops, look at that. I forgot a colon on my validation function. So validate. All right. So with that said, let's go ahead and test. Let's go ahead and actually train the data. All right. So what we're going to do is we're going to run all of this data through our model. And the process of running all the data through the model is called an epoch. So how many epochs do we think it's going to take in order to train this data? And right now, I am familiar with this model, and we're going to know that it takes about 5 epochs in order to run through all this over and over again. So we're going to say epochs equals 5. And so for epoch in range epochs or epochs, and we're going to print out which epoch we're looking at, colon, inside of here, we're going to call this epoch, get it in there. close that and finish this. Okay, we'll close the epoch. Then we're going to train the data, and then we're going to validate the data. Okay, gang, that's it. So if we are ready, I imagine I've got some typo errors in here. So this is good because this is going to set the pace for the rest of this module and these little functions that we're creating here. We're going to use these over and over again. So let's go ahead and execute this and see what happens. Whoa! It says batch must contain tensors, numpy arrays found in class PL image, and so forth. Whoa, that's crazy. So that's training. Okay, so in training loader for X and Y in training loader. Okay, let me see what is the deal with this training for X and Y in training loader. And let me go ahead and see what I can do in order to fix that. Okay, tech artist, I think I found what the problem of this was, because notice if we scroll all the way down to the bottom, it says default collate, whatever that means. Okay, batch must contain tensors, numpy arrays, numbers, dictionaries, or lists. In Fed, we found a class, and I said, what's going on here? So I went all the way back up to, okay. Here's where we created our data loaders. Training loader equals this. And everything looks fine, but then I realized, wait a second, we never told how to transform the data. Okay, but looking backwards, we said, okay, go back up, way back up here. Okay, we define this variable here called transformer. And this transformer says, okay, we've got a transforms, we've got an image, and what we're going to do is we're going to transform that image into a data type, which is float32. So it means it kind of turns it into all this stuff. And we did it here to our test tensor, but we forgot to do this to the data. Oh my golly. Okay, so what that means is we got to go through and we've got to insert more information here. We've got to modify our training loader and our test loader and to transform all that all that gobbledygook information. So go ahead and hit this little plus X cell. It's going to insert a cell before this. And we're going to say training data dot transform. Yep, there it is. Transform equals, and we want to use our transformer variable that we had created just so earlier. And then we're going to do the same thing here to test data. Dot transform equals transformer. Okay, but let's see, this was cell number, no, well, actually just going to do cell 13, and we're way off at cell 34. Okay, so the best thing to do in this situation is we've got to execute all of these over again. And instead of just starting over here and just say, okay, please just re-execute this, 1, 2, 3. Okay, all this, we could just do that. But a fast way of doing that is just clicking over here, and we're going to say, click this one, and go over here to kernel, restart kernel, and run up to selected cell. So it's going to run up to this cell and this one, and say, yes, restart. And hopefully, we can actually watch it progress. And, oh, there it goes. Did it finish? No, not yet. I think it finished. Yeah, that finished. Okay. Yeah, everything finished. So yeah, 13, 14, yep, everything finished. Too busy talking and yapping. Not enough time getting done. Okay, so it goes to, we notice it goes 29, 30, and then 35. All right, so let's go ahead and execute this again. I have a hunch there'll be more errors again, but well, lo and behold, let's give it a shot. I'm gonna go ahead and hit Shift Enter. Whoa, and we got another error, yes. Okay, our accuracy, train and not defined. Okay, So I know that we said, oh, it's called training n, test n, and training n. Okay, we did take a look at this, and so it's not train n, it's training n. Training n. All right, so let's execute this one, and now let's execute our epochs. And it's thinking, bum, 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 and it's going. And it's thinking, and it's going. Remember, it's got 60,000 data to process. 60,000 is a buku amount, and it's just going on and on and on, and it's just going to be plugging and chugging. And I want to just hold on here and wait and see if we got any kind of well, we got, okay, we are training, we name accuracy is not defined. Accuracy. Okay, accuracy again. Accuracy. Oh my. All right, accuracy. Let's go ahead and make sure that this is spelled properly. And because I did it twice, put it on here, and we're going to put it on here. Okay, let's try to execute this again. Execute this again, and let's execute this again. And if all goes well, then we will have got a successful working model. Keep our fingers crossed. And we're just going to keep on waiting, keep on going. Yep, this should take a little while. This is the reason why we want to work on GPUs, because right now your machine should start to sound like it's a jet engine ready for takeoff. And it's just rearing up and ready to rock and roll. Oh, there you go. So, whoa, okay. So check it out. It trained, and the first time it went through, it got, well, about 3,700 wrong. Of the 60,000, it got 37 wrong. So it's at a 0.68. So it's almost 70% correct. Okay, so it's not that bad. And you'll see that that it's and the valid, and this is from the training, it's about the same. So it's about 68%. So it's going to continue on, and so it's going to go through every time it goes through at epoch. It goes through and it orders that, and oh, there we go. And so it's a little bit better, not much. And hopefully that if we keep on training this data, it's going to get a little bit better. I'm going to fast forward this until we've got a full training regiment in place. All right, we're done finished processing here, and it looks the way we did it. We went through 5 epochs. Now, if we let this go, it will steadily get better, hopefully. Not necessarily guaranteed, but hopefully it's going to continue to get better and better and better. But if we look over here that we've got the training, it's got a certain, but when it's validated, the accuracy, it's going down slowly, but it's certainly good. But it finished off with the loss as about, out of 10,000, it got 611 wrong. And so that means it's got an accuracy of about 0.678. So that means about 70% correct. All right, not terrible, but we'd like to try to see, you know, could we do this ourselves? So what we're going to do is we're going to test this against our Model X. Now we created a Model X in here to just kind of test things out. So we got our X0 tensor, and it's been transformed and it's ready to rock and roll. And so what we're going to do is we're going to look and see and how this actually works. So we're going to put this in, and we're going to see prediction equals model X0 tensor. Okay, so this is the test data that we are looking at earlier, and we're going to take a look at what this prediction looks like. Prediction. All right, let's go ahead and execute this. Whoa! And we got 764 values. Okay, 764 values. But if you take a look at here, we're looking for the ones that have the best values. And so here is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. Okay, so so our model says, well, there's a 17, there's a bet about, there is, about one part in about, well, let's see how we do this. So this is about 24. There's about okay, but there's about a 20% chance that this is a 0, 1, 2. It's a 3. There is a more than 50% chance that this is a 5, and there's like a 1% chance that this is a 9. Okay, so what we're thinking is that this model says that's it's either a 3, a 5, or a 9. So it's going to be one, and we're going to go with the what that has the higher value, and we're going to test that. So we're going to test that to see, okay, what's the final value? So we've got 754 values, but we only want to take a look at the first 10. So we're going to take here prediction dot argmax dim equals 1, and keep dim equals true. And then we're going to take a look at y0. We're going to try to test this, see what this is. Okay, but prediction argmax. Let's see what happens when we execute this. Oh, and it says tensor. Okay, and it says, okay, it's probably going to be a value of 5. Okay, let's double check to make sure what's y0. And y0 is 5. Okay, so our model correctly identified this little test guy. First number that we identified this as a 5, and this is correct. Okay, so now there can be celebration and dancing in the aisles, and we can all relax and have a real good time. One thing I want to try to do is go over the steps that we did in order to create this. I know there was a lot of programming in here, but we're going to start duplicating all this programming over again, and we're just going to use some of the same things over and over again. We're going to basically do this a whole bunch of times until it becomes second nature. But to recap, what we did was we loaded and visualized the data. Then we edited the data. Yeah, remember the transforming? Yeah, that transforming, the step that we forgot. Yep, we forgot to do that officially. We created the transformer, but we forgot to apply it to the data. So we we had edited the data. Then we created our model. Then we compiled our model, and then we trained the model with our data. And then we took it one step further, and then we went ahead and we trained the model with our data, and then we took advantage of that and said, hey, take a look at this. We executed a test data and said, yeah, it works pretty well. We knew it had about a 70% chance of being correct, and actually in this situation, it was correct. All right, so this is really good. I'm going to wrap up this video with just the completion of this script, our very first Hello World script. Don't be intimidated by the size. We're going to start duplicating this data. We're going to start duplicating the script over and over again. This script is actually going to start to go much, much faster every single time around. So I'm going to finish this script, and I'm going to finish up this video, and I'm going to go on to the next video. We're going to learn exactly really what is machine learning. All right, thank you very much. I'll see you on the next video.